Let's look at one more example of sketching curves, and I want to try and look at some behavior that we haven't really seen yet so far. So this one will be a little bit interesting. It's not just another polynomial. So we would like to sketch the graph of the function f of x equals x to the 2/3 power minus 2/3 times x. Remember that another way that I could write particularly this term, this really says the cubed root of x squared, and I think that'll help us later on. But if you want to start this problem off like we did in the last example, it might be helpful again to have all of the derivatives worked out so that we don't have to worry about finding them later. So I'm going to find my first derivative here. And the way that this is written right here is actually pretty nice. We don't need to rewrite it or do anything weird with it. We can just use our power rule. So 2/3 times x to the negative 1/3 power minus 2/3 times, well, derivative of x is 1, so just minus 2/3. So we could leave our answer like that. If you preferred this negative exponent, it might be helpful to write that as 2/3x to the 1/3 power minus 2/3 x, excuse me, just 2/3. There's my first derivative, and it also would be helpful to find our second derivative since we'll be working with that as well. So here, let's see, I'll multiply by my power, which is negative 1/3. So I will multiply by negative 1/3. I should have negative 2/9 times x to the negative 4/3. And then derivative of this term, negative 2/3, well, that's just a constant. So derivative of that will be 0. And again, if we want to rewrite it with a positive exponent, it might be a good idea just because we're going to be doing a decent amount of algebra with this problem. So holy moly, there's a lot happening here. We need to start by looking at our original function, though. Let's start with our original function f of x. So f of x equals, and I'm actually going to use this notation, and I'll explain why in just a second. The cubed root of x squared minus 2/3 x. Think about what I want to take away from this original function is the domain. That's the one piece of information I really, really need it from f of x. And I think if you write this with a radical and as a root, it's much more clear what the domain is. I don't necessarily know what the domain of x to the 2/3 is. Perhaps we don't have a lot of experience working with, say, x to the 2/3, but we do know a little bit more about radicals. We know that, hey, if if the index of the root is odd, which it is here in this case, then it's continuous as long as the inside part is continuous. Well, the inside part of x squared, that's continuous everywhere. So what that means is that I have a domain. Oops. And actually, I kind of skipped over. We said this is continuous everywhere because we have an odd index and this inside part, x squared, that's continuous everywhere. We also need to check this part of our function over here, negative 2/3 x. But I had kind of glossed over that. That's just part of a polynomial. That part's not going to give us any problems. So neither one of our terms is giving us problems, which mean that we're not going to have any issues with our domain. Our domain will simply be negative infinity to positive infinity. This is by far the easiest case. We'll look at some examples in section 4.4 where perhaps we don't have a domain of negative infinity to positive infinity. So all right, we've got our domain. Let's start with our first derivative. So f prime of x, I'm going to write this as 2/3x to the 1/3 minus 2/3 here. And I want to think about places where my derivative is 0 and places where my derivative is undefined because I'm trying to find critical numbers. So f prime of x is equal to 0. Let's consider that case first. So 2/3x to the 1/3 minus 2/3 is equal to 0. I'll add 2/3 over first, so this is 2/3x to the 1/3 equals 2/3. Here I don't like using this term or using this process, but it's very convenient here. I'm going to go ahead and cross multiply here. So I will have 6x to the 1/3 equals 6. And then dividing each side by 6, I have x to the 1/3 equals 1. And then the way I would solve this, I would need to cube both sides. I would need to cube both sides, but 1 cubed is simply just 1. So there is my first critical number. I have x equals 1. And again, I know that's a critical number because my domain is negative infinity to positive infinity. X equals 1 is certainly in the domain of our function. I also need to worry about places where f prime of x is equal to 0. And here I am going to have an issue because if you look at this derivative right here, in particular, I'm going to point out this denominator right here. If that denominator is a problem, whoops, we already did f prime of x is equal to 0. I meant f prime of x does not exist. I'm still looking at the same part though. Because if this denominator is 0, then that first derivative is not going to exist. I can't divide by 0. So I'm just going to take this denominator. I don't care about this one over here. I don't care about that 3 on the right-hand term, just because it doesn't have an x. That 3 will never be 0. But this 3x to the 1/3 on the other hand, yeah, that could be 0. This doesn't have an x. It's not a problem for us. So I'm going to take 3x to the 1/3, set it equal to 0, and solve for x here. So we'll divide by 3. I have x to the 1/3 is equal to 0. Again, if I want to solve this equation, I'm going to cube both sides. So I have x equals 0. So here's an instance where when we consider the possibility or the case where f prime of x does not exist, we actually ended up with an x value. This is why having this is so important. So okay, we know it does not exist at 0. All right, these are our two critical numbers. We've got 0, we've got 1. Let's construct our number line here. So f prime, we've got two critical numbers. Here's 0, here's 1. So I want f prime of, let's say, negative, how about negative 1? That would probably be easiest to work with. And again, I'm going to plug that into my derivative, my first derivative, f prime of x. So this will be 2 over 3 times negative 1 to the 1/3 power minus 2/3. And you can go and calculate that. I'm going to go pretty quickly through that. I should end up with, I believe, negative 4/3 or negative 1.3 repeating if you're the decimal type. But what's important here is the sign. It's negative. So my first derivative is negative. That means my function is decreasing on that interval. So next, this one's a little bit tricky because I need a number between 0 and 1. Between 0 and 1, I'm going to go ahead and pick 1/2 or 0.5. You can even use 0.5 if you'd like. There's really not a great candidate. But I'm going to plug that into my first derivative just like we did before. I'm not going to write that whole thing out. I'll let you do that if you'd like. But here, if you want a decimal, I have 0.173 repeating. Again, really the thing I want to take away from this is the sign. It's a positive, which means that my function is increasing. So okay, that's very good to know. Now, I need a number on the right-hand side of 1. Again, I'm going to plug that into my first derivative, f prime of x. So f prime of, let's say, 2. And again, we can take that, plug that into our function. Here, this time, I end up with negative 0.138. Because we end up with a nasty cube root of 2. And really, no matter what number you pick, it's not going to be great. Negative 0.138. Here I have a negative, and my function is decreasing here. So this is really cool. The one thing actually I forgot to do earlier, and let me fix that now, is I didn't talk about the behavior of the derivative at 0 and at 1. So let's fix that really quickly. At 0, we found that by saying that the derivative does not exist. So at 0, I'm going to make a little note to myself that my derivative does not exist. How did I find 1? Well, 1 came from setting the derivative equal to 0. So 1, I'm going to put a little 0 right above it. So this is really cool. We have this instance here where our function is decreasing and then increasing, and our derivative does not exist there. However, if you look at that point in the domain, 0 is in the domain of our function. And what this means, even though the derivative does not exist here, at x equals 0, we're still going to have a minimum. We still have a minimum at x equals 0. The behavior of that minimum is going to look quite a bit different from what we're used to seeing, though. At 1, we have a derivative of 0. This is the horizontal tangent line. This is by far what we're a lot more familiar with here. So let's summarize this up. We know our function is increasing. It's increasing on the interval 0 to 1. It is decreasing everywhere else. So it's decreasing on negative infinity to 0 and 1 to positive infinity. We should also find the locations of these local extrema. So I'm going to do that just off to the side here, f of 0. And for 0, I'm looking back at either this rewritten version of the original function or just the original function that they gave you. I'd probably go to that and just not overthink it. And actually, let me just give myself some room. So f of 0, this is 0 to the 2/3 minus 2/3 times 0. Here I'll get 0. So we said at 0, what's going on here? It's decreasing and then increasing. My graph might look something like that. I have a minimum, so local min at 0, 0. At 1, if I go back and look over here at 1, here my function is increasing and then decreasing. We've got that classic horizontal tangent line. That is a local maximum. So we do still need to find the coordinate there of 1. And to do that, I'm going to take 1, plug that into my original function. So f of 1, this is 1 to the 2/3 minus 2/3 times 1. Here I should end up with 1/3, 1/3, or 0.3 repeating if you're the decimal type. So we have a local max at, we'll say 1 comma, and we'll say 0.3 repeating. So we haven't even gotten to our second derivative yet, and we've seen all sorts of cool stuff happen. Just to kind of recap everything, we found our domain. We said it was negative infinity to positive infinity. We found out our function is increasing on the interval 0 to 1. It's decreasing everywhere else, which means that we have a local minimum at 0, 0. We have a local maximum at 1, 1/3. Excellent. The good news is this problem isn't even over yet because we got to talk about the second derivative now. So okay, now let's talk about the second derivative. So here let's just rewrite it so that we have it handy. F double prime of x here we said was negative 2 over 9x to the 4/3 power. So negative 2 over 9x to the 4/3 power. Here, again, I'm going to start this problem just like I have pretty much every other time. I'm going to look for partition numbers for my second derivative. So I'm going to take my second derivative, and I'm first going to say, all right, well, where is my second derivative equal to 0? Here, in this case, something interesting happens. We have negative 2 over 9x to the 4/3 is equal to 0. If I want to solve this equation, I can't do it with this power of x in the denominator. So I'd have to multiply both sides by 9x to the 4/3 on each side. 9x to the 4/3. Look at what happens on the left-hand side. These two will just cancel. I'm left with negative 2. On the right-hand side, well, 0 times anything is just 0. So I should just have 0. last time I checked, -2 is not equal to 0, which means that this equation has no solutions to it. So I ended up with no partition numbers when I took my second derivative and set it equal to 0. But that's okay, because we still have one other possibility. We could also have the possibility where f double prime of x does not exist. Does not exist, or is undefined. Here, it's going to be this denominator again that causes a problem. Usually, if you have a place where your first or your second derivative does not exist, it's the denominator, it's dividing by 0, that's going to give you a problem. So I am going to take that denominator, 9x to the 4/3, set it equal to 0, and solve for x. Dividing by 9 is how we'd start. It still just gives us x to the 4/3 is equal to 0. And if I wanted to solve this equation, I want to talk about that for just a second. If I raise each side to the reciprocal power, so if I raised each side to the 3/4 power, that would also still give me 0. So I end up with x equals 0. 0 to any finite power over here will always be 0. So what that means is 0 is my only partition number. So when it comes time to look at our second derivative, f double prime, we've got 0. And then now we need to test numbers on either side of 0 by plugging those into our second derivative. So how about we use -1, +1? That seems like the easiest way. F double prime of, how about -1? This is -2 over 9 times -1 to the 4/3 power. So let's see, if I take -1 and plug this in, I end up with -0.2 repeating. I believe that's just -2/9. Let me double check. Yes. So it's -2/9. But again, it's the negative sign that I'm really interested in. My second derivative is negative. My function is concave down. Well, what about on the right-hand side of 0? How about we take 1 and plug that in? -2 over 9 times 1 to the 4/3 power. This time I'll end up with, well, the same darn thing, -0.2 repeating, or -2/9. So on the opposite side, my function is still concave down because my second derivative is negative. So let's look at this. What is this telling me? Well, first of all, it's telling me it's concave down almost everywhere. Be careful you don't say everywhere. This graph is concave down on -infinity to 0 and 0 to infinity. It might also be a good idea just to make a note. Hey, how did we find this x equals 0 right here? Well, we found that by saying f prime of x does not exist. So you may want to make a note to yourself that, hey, at 0, our second derivative does not exist. And that might help you remember then that 0, technically the graph is not concave down there at 0 because it has no concavity. Something odd is happening at 0. It's not concave up anywhere. It's always concave down. So that's kind of neat. And then where does our graph change, or excuse me, where does our second derivative change sign? Where's the inflection points? There are none. Look at this. It's negative on the left-hand side of 0. It's negative on the right-hand side of 0. This is kind of an interesting graph that we haven't seen. We actually have no inflection points because the second derivative never changes sign. So no inflection points. This is everything important. Oops. This is everything important that I think I can get from the second derivative. And we're running out of room, so we're just gonna go into the next problem. So let's summarize everything that we've talked about here, because we found out a lot of information here. We need to talk about our domain. We said the domain was -infinity to +infinity. We said that, oh boy, I have to go back and look. We said our function is increasing on 0 to 1, so it's increasing on 0 to 1. It is decreasing everywhere else, so negative infinity to to 0, and 1 to positive infinity. We said we had a local min right here at 0, 0. So we have a local min at 0, 0. A local max at 1, I believe 1, 1/3. Yeah, 0.3 repeating. 1, 0.3 repeating. The graph is concave down. We just found that. Concave down on negative infinity to 0 and 0 to positive infinity. And there are no inflection points. Sad face. Oh boy. What might be helpful in these problems is, honestly, I might try and summarize all of this key information that we're finding along the way. Find a spot that you can do that on your paper. So maybe keep your margins clear, or honestly, maybe even just do it on a separate sheet of paper, just so that it's easy to find later. You don't need to kind of restate everything that you found. Although alternatively, perhaps it's helpful to restate everything that we found, just so that it's all fresh in our mind. But I would recommend that you just keep really good track of this, no matter how you go about it. All right, so now we got to sketch the graph of this guy. This one is interesting. Few things I'm going to look at. Domain, this time again, negative infinity to positive infinity, and really what that tells me, there's no holes, no breaks, no asymptotes, nothing that we would maybe consider traditional odd behavior for a graph. So it's helpful for us in that sense, but not very helpful. The thing I'm going to point out, I always think, the local extrema are probably the most helpful points. Those are always the ones I fall back on. So we have a local min at 0, 0, and I'm going to make a note again that, hey, that's a minimum. And then at 1, 1/3, so let me label a few points right here. Actually, here, let me give myself more room, because this graph is relatively small. So here's 2, here's 3, and that's really all I need to know. So I've made my local min at 0, 0. That's good. And I'm going to plot my local max at 0, 1/3, 1, 1/3. So I should have a point, let's just say right around here. And again, I'm going to make a note to myself, that that's a maximum. You may also want to, when you're talking about your min and your max, I would also recommend going back to your sign chart. Look at what the derivative is doing exactly at those points. Because right here at 1, that's where we have that nice horizontal tangent line. 0, well, something odd is happening at 0. We still haven't quite figured it out. But at 1, I think it would be helpful to make a little horizontal tangent line for yourself, so that we know, yeah, there's a horizontal tangent line there at 1. I know exactly what the behavior is going to look like. So, okay, we've talked about min and max. Next, I would normally say, well, let's talk about your inflection points. There's only one problem, is that I don't have any inflection points. So that's not really going to help us here. The other thing I really like to rely on is your concavity, because that tells you a whole lot. Remember, when you write in these min and your max, you're already talking about where your function is increasing and where your function is decreasing. I don't think you necessarily need to revisit that, but you can if you want to. It might be a nice way to check your work, but this is what I'm going to look for as a concavity. We said our graph was concave down pretty much everywhere except for 0. Not concave down or concave up at 0. Something odd is happening at 0. So let's just look at each side one at a time. What about the left-hand side? It's concave down. Now I'm going to draw a graph which is concave down, and I'm going to purposely draw it wrong. Oops. something like this. Oops, that's not even very good. How about that? Nope, didn't draw that time. There we go. There you go, Mr. Huber. I drew a graph that's concave down. Say, well, you sure did, but there's a problem with it. And it's this point right here. What's happening at that point that I highlighted? It's a maximum. We didn't find any maximum on the left-hand side of the y-axis. We didn't find any local extrema over here. We only have the two that we found. We have this minimum here and this maximum here. So that means our graph can't possibly look like the one that I've drawn right now. It just can't. Because otherwise we would have found another maximum. This one's very odd in that it's concave down, but it's always, and you can actually look at this part right here, it's decreasing. It's concave down and decreasing. So, oops, again, my graph is going to look perhaps something like this. It might level out, and as long as it's still decreasing, that's totally fine. But perhaps it looks something like this. It's concave down once we get to that point. Well, what about afterwards? What about on the right-hand side of 0? On that right-hand side of 0, it's also concave down. So we have this concave down. We drew in that horizontal tangent line, so I think that's really helpful to identify, okay, there's our maximum. And then after that, it needs to continue decreasing. It's going to look something like this. So this is kind of interesting. We haven't seen a graph like this in a long time here. We have a what's called a cusp right there at 0, 0. Technically, the slope of the tangent line there is vertical, which is why the derivative does not exist there. So you can still have this point 0, 0 be in your domain because it sure is. But the derivative does not exist there, which leads to some really interesting behavior. That's why we have this cusp here. So this is a really nice example to look at. It kind of goes a little bit more in depth into into kind of a simpler root function, which I think will be really handy for you when you work on the homework. Last thing I'm going to talk about here, I was going to save this for another video, but I want to just mention this here, is that we've now talked about the original function, the derivative, and the second derivative, and it can be difficult to keep all of those three things straight in your head as you're working through problems. Remember that f of x tells you the y value of the function at a given point. So we use this to find the point on our graph. So if we're looking for if we want to plot a point on our graph, take the x value, plug it into the original function. The first derivative tells us the slope of the tangent line at a given point. So this tells us something different. It tells us the slope of the tangent line. We use this to help us find local extrema and intervals where our function f is increasing or decreasing. So it tells us a little bit, it tells us where our function is increasing or decreasing or the slope of the tangent line. We do not use it to find a y value. That's what f of x is for. And then, of course, to complicate matters further, we have our second derivative. This tells us the concavity of the function at a given point. And right now, we're just going to focus on concave up or concave down. Is it positive or is it negative? Or perhaps 0. We use this second derivative to help us find inflection points, intervals where f is concave up or concave down. So we're not going to use it to find slope of the tangent line. We're not going to use it to find the y value. That is what these other two guys were for. So at the end of this, I just want to say be careful as you're juggling all of these different functions. You've got your f of x, you've got your f prime of x, you've got your f double prime of x. They all tell you different things. And that's an easy part to overlook and an easy thing to get wrong going forward is to mix those up. So try and keep these straight in your head. I would recommend copying this down on a sheet of paper and just having this next to you as you work through the example problems or the practice problems in 4.2 and in the next section in 4.4 as well.